By now you should be familiar with the periodic table and how it organizes elements according to atomic number and by grouping elements that have similar properties. When we look at the periodic table more closely, we notice several interesting trends called periodic trends. The trend we're going to look at in this video is an interesting pattern we see in the size of the atomic radii as we move across the periodic table and as we move down a column. Let's define what we mean by atomic radius. As you may recall from math class, radius is generally defined as the distance between the center of the circle and the edge of the circle, or 1/2 the diameter. Because electrons are moving around in clouds of probability, it's very difficult to tell where the edge of an atom is. Hence, atomic radius is defined as 1/2 the distance between the nuclei in a molecule consisting of two identical atoms joined by a covalent bond. A little complicated, but this is how it's defined. We use atomic radius as a measurement of how large or small an atom of a particular element is. Now, you would expect that as we add more protons and electrons, our atom would get larger, right? If we graphed atomic radius on the y-axis and the atomic number on the x-axis, maybe we would get some sort of a line or curve moving in the upward direction as we went from left to right. But this is not what happens. Our graph looks something like this. On the x-axis, we have atomic number. That is determined by the number of protons. On the y-axis, it says empirical atomic radius. Well, that is just the atomic radius. And when we look at this more closely, we see a zigzag pattern like this. Well, let's look at this segment here, and let's see if we can figure out what this means and why this is like this. This line here represents the radii of the atoms in the second period of the periodic table. Let's start at the first element in this period. That would be lithium. We notice that as the atomic number increases and as we go from left to right across that second period, the atomic radius goes down. The atomic radius is getting smaller as our atomic numbers increase. And then, look here, we notice that there's a bump, and all of a sudden, the atomic radius gets very large again. The main thing that has changed here is that we've gone down to the next row or period of the periodic table. Lithium was in the second row, and sodium is in the third row. As we work our way across the third period, we see a similar pattern. As the atomic number gets larger, the atomic radius gets smaller. And then, all of a sudden, the atomic radius goes up again. When we get to potassium, notice that potassium is in the fourth row. But just like with the other two rows, as we go across that row, that period, the atomic radius gets smaller. It doesn't get larger. And then there's another increase in the size of the radius when we get to rubidium. As you can see, this trend more or less continues as we move down from period to period. The radius gets smaller as the atomic number increases. Let's take a look at the pattern that happens as we go down a group. Notice that as we go from lithium to sodium to potassium to rubidium, etc., as we move down a column, the atomic radius increases. Why do these trends happen? Why are all these blips or rapid jumps in size happening every time we get to the start of a new row? Well, each time we get to a new row, we are adding another shell, another energy level. Take a look at this wonderful little simulation from javalab.org. Let's look at hydrogen. Notice that there is only one shell, only one energy level. And when we move down the column to period 2, where lithium is, notice that we add a new energy level. This one is farther out. The distance is greater from the nucleus. So it's not surprising that the atomic radius is a little larger than it was for hydrogen. Now let's go down to another period. Once again, when we look at sodium, we've added a new energy level, and the atomic radius for sodium is larger than it is for lithium. We see this again for potassium and rubidium and cesium and francium. Each time we move down to another period, we add another electron shell, and each new energy level is farther from the nucleus than the one before it was. The atomic radius therefore gets larger as we move down a column and add new energy levels. Now, this is what we might expect. The atoms are getting bigger. They're adding more protons and electrons, right? But now, let's look at what's happening when we move across a period. In order to understand what's happening here, we need to remember the forces that are pulling and pushing on the electrons inside the atom. Remember that electrons have negative charges, and they are attracted to the protons in the nucleus, which have positive charges. They're also repelled a little bit by other electrons, since like charges repel each other. But it's the positive charge of the nucleus that we really want to focus on right now. Before we go any further, I want to go over some vocabulary. When we talk about periodic trends, there are two types of electrons we like to talk about. Valence electrons are the electrons in the outermost energy level or shell. As we can see from this model, potassium has one valence electron. The electrons in the inner shells, or energy levels, are called core electrons. In an atom, there's a balance between the pulling force of the positive nucleus on the electron and the small repelling or pushing force that electrons exert on each other. The attractive force from the protons generally wins out because the shielding force is usually not very big. Effective nuclear charge is the term we use to talk about the amount of charge the electron really sees. It's the attractive force of the protons in the nucleus minus the shielding or repelling forces of the core electrons. So let's talk about how all this stuff affects atomic radius inside a period. We'll look at the second row elements again, starting with lithium. There are 3 protons in the center. There are also some neutrons, but I'll just symbolize them as a big gray circle here so we can focus on the protons. They're what's important here since the neutrons don't have any charge and they don't put any force on the electrons. There are 2 core electrons in the first energy level and 1 valence electron in the second energy level for lithium. This valence electron here feels an attractive force from the positive nucleus. It also feels a tiny repelling force from the 2 core electrons. Although the attractive force from the nucleus still predominates, the shielding effect of those electrons diminishes or lessens the amount of attraction the electron feels just a little bit. So the effective nuclear charge is a little less than what the electron would feel if there were no core electrons. Okay, so we've looked at our lithium atom. Now, let's add a proton to make the element beryllium. We'll also add an electron to keep the atom neutral. Now, beryllium has 4 protons in it. Both of its valence electrons are seeing the same core electrons that the electron in the lithium atom did. So the amount of shielding is the same as it was in the lithium atom. However, these valence electrons are seeing a larger positive charge than the electron saw in lithium because we have 4 protons in the nucleus instead of 3. Remember from a prior video that the greater the charge, the greater the force of attraction. The greater positive charge pulls in the electron shell. It pulls it a little closer than it was in the lithium atom. Therefore, the atomic radius is a little bit smaller. Let's add another proton to make boron. We'll add another electron too. Once again, boron has the same 2 core electrons that lithium and beryllium did. And so the amount of shielding is pretty much the same as it was for the other 2 atoms. However, because it has 5 protons now, the effective nuclear charge is greater than it was for the other 2 atoms. All of the electrons are pulled in tighter, and the atomic radius gets a little smaller. Let's add another proton, and we get carbon. This pattern continues. All of the atoms in this period have the same 2 core electrons, and so the shielding is about the same. However, as you move from left to right, the number of protons gets larger, and the effective nuclear charge increases. And the electrons get pulled in tighter, and the atomic radius gets smaller. Finally, when we get to neon, the outer shell is full, and neon has the smallest atomic radius in this period. When we add another proton to make sodium, since the shell is full, we need to add another energy level for a new electron. And this makes the atomic radius larger, and this explains the blip we see on our graph. Let's look across period 2 without all the arrows. See that the atomic radius gets smaller and smaller and smaller as the effective nuclear charge increases. And we're going to do this one more time. We're going to just represent the charge in the nucleus with only numbers. We start with the first period, which only contains hydrogen and helium. Helium is smaller than hydrogen because we have added another proton. When we get to lithium, we have to add another energy shell, and the radius increases. As we march across the period, we increase the effective nuclear charge by adding more protons. This pulls the electrons tighter towards the nucleus, and the radius gets smaller. Once we have filled the second energy level, we have to add a new one, and the atomic radius will get larger because of this. We're now in period 3. And as we move across period 3 and keep adding more protons, the increasing effective nuclear charge continues to pull the electrons in, and the radius gets smaller until we have filled the third shell. Then we add another one, and we're in period 4. The radius is larger again because we have added more shells. There's one other thing I want you to look at in this animation. Notice that as we add more protons, the core electrons keep getting pulled in more and more and more and more. But even though this is happening, the atomic radius still gets larger as we go down a column because we're adding new shells. So let's summarize. When you look at the elements in the periodic table, you see that the atomic radius gets smaller as you move from left to right across a period. This is because as you add protons, the effective nuclear charge, the charge the electrons see, is getting larger, and it's pulling the electrons in more tightly. As you go down the columns, however, the radius keeps getting bigger. This is because with each new row, you add another energy level.